In a spring-loaded governor of Hartnell type, the mass of each ball is 5 kg. So this is your small m. The lift of the sleeve is 50 mm. Total h, small h is 50 mm. The speed at which the governor begins to float is 240 rpm, n1, lower speed. And at this speed, the radius of ball path is 110 mm. This is r1. Okay. The mean working speed of the governor is 20 times the range of speed when the friction is neglected. If the length of the ball and the roller arms of the bell crank lever are, this is ball arm is x, roller arm is y. X is equal to 120, y equal to 100 respectively. And if the distance between the center of pivot of the bell crank lever and the axis of rotation is 140. So this is center of pivot of the bell crank lever and axis of rotation is r. Okay, is 140. Not R1 or R2, it is R. Determine the initial compression of the spring taking into account the obliquity of the arms. If friction is equivalent to a force of 13 Newton at the sleeve, find the total alteration in speed before the sleeve begins to move from its position. Okay, so let's list down the given data. So m equal to 5 kg, small m, ball mass is 5 kg, compression of the spring is 50 millimeter, initial lower speed is 240, omega of that is 25.14. So this is actually R. For that particular RPM, the radius of rotation is 110 millimeter. So obliquity, the arms, ball arm is X. The ball is here, therefore this is your ball arm X. Okay. So ball arm is 120, sleeve arm is 100, and the pivot point radius. So from here to governor axis, it does not change in both the cases. It remains same. R is same. Okay. For both the cases, R is same. See here. So from this pivot point to R is same for both the cases, irrespective of any position of the governor. Okay, so these are the questions. Let's move into the problem. Initial compression of the spring taking into account the obliquity of the arms. Okay, first of all, let us find out the maximum speed of rotation omega 2. We know that this is the average speed omega 1 plus omega 2 by 2. Range of speed is omega 2 minus omega 1. Difference between the maximum and minimum speed is called range of speed. Okay, so given that mean working speed is 20 times the speed range, that is one condition given in question. One confusing sentence is there in the question which tells you that the range of speed, 20 times the range of speed is the mean working speed. It's a condition given in question. Therefore, I am taking that. So this is the range of speed. Multiply this by 20, you will get this. Okay. So I am going to equate that. So omega equal to 20 into omega 2 minus omega 1. Out of this, I don't know omega 1. Omega also I know. Omega 2 also I know. Therefore, so omega 1 plus omega 2 by 2 equal to 20 into omega 2 minus omega 1. So put all the values into that, into this equation. Okay. Which equation? Here. Omega 1 is known to me. Omega 2 is unknown out of this equation. Okay. So put all the numbers and solve for omega 2. Omega 1 is 25.14. Put it into the above equation. So 25.14 plus omega 2 equal to 40 into. So out of this, if you solve for omega 2, you will get omega 2 as 26.43 radians. Okay. So minimum and maximum position of the ball is shown in figure A and B respectively, right? So let R2 equal to maximum radius of rotation here. So ball center to spindle axis when the governor is tilted outside due to higher centrifugal force at a higher RPM. R2 is the maximum radius of rotation. Lift of the sleeve H is equal to R2 minus R1 into Y by X. So R2 equal to R1. R1 is given in question 110 millimeter. Okay. So this R1 is given as 110 millimeter in question. Okay. So R1 plus H into X by Y. So R1 is 110. Sleeve lift is given as 50 millimeter. Y naught by XY values are given 12 millimeter, 120, 100. So I can find out the value of R2, 0.17 meter. Okay. So both the cases centrifugal forces you find out. Ball mass, omega 1, omega 2 you know, mass you know, R1, R2 you know. Find out the two values of centrifugal forces. M omega 1 square R1. So mass of ball mass is 5 kg, omega 1 is 25.14 given in the question itself. Okay. So I have 110 RPM for that case, 347.6 Newton. Second case, FC2, omega 2 just now you have found out using equations 26.43, omega 2 square, ball mass is 5. R2 just now you have found out as 0.17, it comes around 593.8 Newton. So two centrifugal forces I am finding. Since the obliquity of the arm is to be taken into account, minimum, so take this minimum position. What is the obliquity here? So normally what we do, we take x1 equal to x and solve the problem. Okay, this height variation is not considered. If your L is here, if your there is no deflection, the mean position of the governor is here, the height will be larger than when it is tilted, correct? Now this difference is normally neglected. Now we are going to consider the difference. So that's why you are going to consider obliquity. So x by y, wherever you have x by y, there you have to do x1 by y1. Wherever you have that, you have to do x2 by y2 for the higher speed case. So x1, y1 and x2, y2 you have to find out. Then substitute those values into the equation. That is what considering obliquity. Clear? Okay. So here in this diagram you look carefully. A1 equal to, what is A1? This is A1 equal to this total distance minus this, correct? So what is that? This is R, this is R1. Similarly for the other case what will happen? That we will look there. So this you understand. So A1 equal to R minus R1. So both values you have, find it out, 0.03 meter. Okay. So what is that? A1. A1 now, this A1 is this length. So this length is nothing but, now I can make a triangle like this. With this side as A1, this side as X. So X also I know, A1 also I know. Now I can find out X by Pythagoras, X1 by Pythagoras theorem. Clear? So that is what you are finding A1 for. From figure we can write x1 equal to by Pythagoras theorem, x square minus a1 square. So x is 0.12, a1 is 0.03. How a1 0.03? Just now you have found out here, r minus r. Okay. Time is running out. We'll move fast. So find out the value of by Pythagoras theorem, finding it as x1 as. Similarly for the y case also you are going to find out y1. y1 equal to y square minus h1 square. Look at this triangle. So y square minus h1 square will give you y1. Considering obliquity means instead of xy everywhere you are going to for lower case x1 y1, higher case x2 y2. x1 y1, x2 y2 you have to find out by Pythagoras theorem from the diagrams. Okay. So y is 0.1, h1 is 25 millimeter, half of the full deflection 50. I am taking 25. So that I am substituting and I am finding out y1 as 0.0986. So x1 y1 values also you have to consider. Okay. That is considering obliquity. x1 is y1 is the values 1162, 0.0986. Now similarly for maximum position, here also I am going to do the same thing. A2. Where is A2? A2 is here. So this is R2 minus R. Always larger minus smaller. Initially it was R minus R1. Here it is R2 minus R. Because R2 is greater than R, you have to subtract R. Here R2 minus R. You don't have to by heart that. Just look at the larger minus smaller will give you this. Then using that you are going to do Pythagoras theorem. Okay. To find out the obliquity. Okay. So I am finding out same 0.03. So same Pythagoras theorem I am finding it out as x1 as 0.1162. Similarly y2 the Pythagoras theorem in the lower triangle. So I am getting it as 0.0986. It happens to be the same. It is a mirror image, symmetric. Initial and final also I am getting same x2 y2. x1 y1 equal to x2 y2 in this problem, because the two positions given are symmetric, mirror images about the mean position. Otherwise it will not come like that. Okay. So now just few minutes I will complete. So now taking a moment about the point O in this diagram. So this formula, this is general formula. Okay, this formula comes by taking moment only. So this normally we neglect this portion. Okay, this ball mass portion we neglect out of the calculation initially. Now we are considering that because you have A1 everything in this problem, we are considering that. You go back to the initial derivation, you will see this is the general formula. Okay, so mg plus s1 by 2 into y1. This is the general formula of Hartnell governor. Most complex formula. Okay, this is there in the derivation video. You go and see that. So now taking m is equal to 0. Sleeve mass is not given in the problem. Therefore taking m is equal to capital M equal to 0. So x1 is 0.1162. Y1 value is there. Mass is 5 kg. A1 is value is there. FC1 value is there. Put all the values into this. So now since capital M is not given, I am taking it as 0. Therefore it vanishes. So S1 by 2 into Y1 value. Y1 is 0.0986 equal to. So FC1 is 347.6. This initially you have found out into X1 minus ball mass 5 kg gravity into A1. A1 is 0.03. So I can solve for initial load on the spring 804 Newton. Similarly, I am taking the second diagram, maximum position, and solve for S2. All the 2's you substitute and find out S2. Okay. So taking M equal to 0, X2 is 0.1162, Y2 0.0986, M 5 kg, A2 is 0.03, FC2 is 593.8. You go back to previous slides and see centrifugal force of second case, omega 2 r omega 2 square R2 into ball mass. Okay, M omega 2 square R2, that is 593. So M is, capital M is taken as 0, this term vanishes, therefore S2 by 2 into Y2 0.0986, the FC2 is 593.8, X2 is 0.1162, ball mass is 5 kg, gravity A2 0.03. So on solving this I will get S2 equal to 1456 Newton, right? Stiffness of the spring S2 minus S1 by H. S1, S2 values just now you have found out. H is 50 millimeter substituted. So 1456 S2. S2 minus S1 by millimeter itself I am substituting the H. So I am getting 13.04 Newton per millimeter as the stiffness of the spring. Second question, initial compression of the spring. S1 S1 by S. So 804 by 13.04, 61.66 millimeter. So initial compression of the spring is 61.66 millimeter. So second question, total alteration on speed when friction is taken into account. So you have a special formula for this, you have to make a note of that. So S1, S is equal to S1 plus H1 into S. So load on the spring I am finding out, S1 plus H1 into S. So this is the lowest speed plus deflection for the first half into stiffness. So that gives me mid position load on the spring. The load on the initial case plus deflection up to mid position multiplied by stiffness. So that gives me load on the mid position. Okay. So this is not a formula. This is a general common sense equation. You can write this yourself. So 804 plus 25 into 13.04, it gives me 1130 Newton is the load on the spring at the mid position. Okay. So angular speed, omega, mean speed. Find out the mean of the two omegas. So corresponding value of n you find out, reverse that, 246.2 rpm. So speed at which the sleeve begins to move downwards from the mid position, this formula you make a note. Okay. So from the mid position there is some cushion, plus or minus 1% or 2%. So that due to friction at what speed, so mean position speed is 246.2, and from that speed some plus 1 or 2 rpm it will remain in the same position due to friction. Now what is that speed? What is the minimum speed after which the sleeve goes down? Maximum speed after which the sleeve moves up from this equilibrium L position of the governor arm. Okay. So for that the formula, you note this formula, n dash is equal to, this is the lower case speed because friction is subtracted here. Okay. So n into square root of S minus F by S. Okay. So this is the equilibrium speed, 246.2 mean speed, into stiffness. This is the load at the on the spring at the mean position. Just now you have found out 1130. Friction is 30 Newton. So substitute all the numbers into this. You get 243 rpm. So if we go less than 243 rpm, this arm will no longer remain vertical. It will go inside. As long as you are at from 246 rpm, actually 246 rpm is the theoretical speed at which your arm will remain like this. So as long as you are at least 243 rpm, it will remain like this. Below 243, it will go inside. Okay. Similarly on the higher side, so just change this to plus, you will get the higher side of that. So maximum speed, so sleeve begins to move upwards beyond the speed. At what speed? So plus friction, n double dash, that comes from 249 rpm. Okay. So from 243 to 249, your sleeve will remain exactly like a vertical L. Okay. Below and above that it will change. So that is plus or minus 6 rpm is the alteration of speed, n double dash minus n dash, 249 minus 243. So this formula is very special. You have to note down. It is used very rarely. The n dash is the lowest possible speed for equilibrium position, highest possible speed for equilibrium position. 6 rpm is the difference in the speed between the two, right? So I sum up the results. Initial compression of spring 61.66 millimeter. Alteration of speed due to friction is 6 rpm. Plus or minus 6 rpm. The friction is stopping. Okay, that completes the problem. So it's taken from a Gurmit textbook 18.